could draw initially. So we'll call this the Sprite, beer, Diet Coke. Okay. And each of them has a probability of 6 out of 18 cans of getting chosen. And notice that if you add the 3 probabilities, you get a sum of 1. Now, if we drew a Sprite first, okay, let's see what'll happen. So if we drew a Sprite first, we could get a Sprite, a beer, or a Diet Coke again, right? Well, on this draw of the tree, since we drew a Sprite the first time, there's only 5 Sprites left out of 17 cans of soda, or 17 cans of beverages. And here we still have 6 cans of beer out of its total of 17, and 6 cans of Diet Coke out of 17. All right, let's now look at the beer, right? So with the beer, you could get a Sprite, another beer, or a Diet Coke. Out of 17, since you didn't draw a Sprite, you did draw a beer the last time, so this would be 5 out of 17. And as far as the Diet Coke goes, you'd still have 6 out of 17. And then coming over to the Diet Coke part, well, what are we going to have? Holy moly, right? We're going to end up with, if we drew a Diet Coke the first time, we'd still have 6 Sprites, so 6 out of 17. And then 6 beers out of 17, but we'd only have 5 Diet Cokes out of 17. So this can get kind of crazy, huh, this model? Hopefully I have room for everything. So I'm just going to finish up pretty quickly and you can follow along, okay? trials, you're going to multiply each of these probabilities for the, draw, and then the draw, and then the draw. There may be other things that we need to take into consideration. So what is the sample space? Goodness gracious. Well, it's pretty long. It's going to be, you could get a Sprite, and a Sprite. So I'm just going to go along. So I'm sort of tracing along. Sprite, Sprite, Sprite. Wow, if you go through every single branch, you get all of these possibilities. So that it really should be in set notation. Why don't we change this since I ran out of room, and we'll say list the sample space. So here, this is all the different things that can happen, all right? So what is the probability that you will end up with 3 Diet Cokes? Well, Diet Coke, Diet Coke, Diet Coke was over here. That would be Diet Coke, Diet Coke, Diet Coke. That's the only way you can get 3 Diet Cokes, by the way. So probability, Diet Coke, Diet Coke, Diet Coke, right, is going to be equal to, I just multiply along the branches. So 6/18 times 5/17 times 4/16. So this ends up being approximately 2.5% if we go to percentage. Or if you did a decimal, 0.025. Good? All right, let's check this following out. What's the probability of pulling out a Sprite on the first draw? So a Sprite on the first draw is going to be, remember we had this here, a Sprite on the first draw is that, right? And so it's going to contain all of these situations here. Do you see? And there won't be any intersection because you won't be pulling 2 cans at a time, right? So what we need to do is find each of these probabilities and then sum them. Isn't this fun? So let's go ahead and do so. All right, so Sprite's Sprite, Sprite is going to be the same as Diet Coke, Diet Coke, Diet Coke. But you know what? I can write all of them out. So this ends up being probability of Sprite, 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 plus the probability of Sprite, Sprite, beer, plus probability of Sprite, Sprite, Diet Coke. We end up with approximately, make that neater, 32.1%. And that isn't surprising, is it? Because doesn't that look to be about a third of the situation here? Cool. What's the probability we'll end up with at least 2 beers? So what does that mean? Well, if there's at least 2 beers, that means you could have 2 or 3 beers, right? So what we need to do is look at all the cases, no pun intended, all of the situations where we have 2 beers or 3 beers. So let's just take a look at, we'll highlight them in this color so we can keep track. So I have 2 beers here. So, writing it out, that's going to be probability of at least 2 beers is equal to the probability of a Sprite, a beer, and a beer, right? Plus the probability of a beer, a Sprite, and a beer. And this ends up being approximately 24.5%. Good so far? I know, that's a scary problem. Don't worry, you wouldn't have a test problem like that. All right, so here we go, the counting rule. For a count of two events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. So if we look at this example 2, how many different 3-digit codes are possible if the first digit consists of a number from 1 to 9, the second digit consists of an uppercase letter, and the third digit consists of a lowercase letter? Well, here's the first digit, right? So this one has to be the numbers, right, from 1 to 9. This is our uppercase. And this one is our lowercase, right? Well, there is, 9 ways to pick this one, 26 ways to pick the last 2. So the total number of codes you would have, and they would be unique because there would be no repeat of anything, would be this product. So let's see what that is. So there are 6,084 3-digit codes possible with these conditions. Cool, cool? All right. And then let's take a look at example 3. I'm giving you this problem on purpose because a lot of times they give this problem like on the GRE, graduate record exam and stuff like that in the quantitative part. So find the number of ways that 4 people can be seated at a round table. Now, the thing to remember about a round table is that since it's round, you can rotate it, right? So what we're going to look at is this. We'll call them just person 1, 2, 3, and 4, right? So let's always have person 1 at the head of the table. All right, so if we have some initial, or not head of the table, but at this part of the round table. So one configuration would be just to go clockwise, right? Where 1's on the top and you go around. If I keep 2 next to me each time, if I want, set it up that way, 2 could stay on this side and we could swap the 3 and the 4, right? And then 2 could be over on the other side, and we could keep the 3 and we could keep the 3 here, and then the 4 could go here, right? Or what else could happen? We could have the 2 on this side, and we could have the 4 here and the 3 here. So now I've explored every situation where the number 2 person is next to the number 1 person. So now we just need to look at the 2 situations where that's not the case. So if we have the 2 across, we could have the 3 here and the 4 here. Or if the 2 is across again, we could have the 4 on this side and the 3 on this side. And so it turns out that there are 6 possible seating arrangements for a round table with 4 people. Okay? So what you may want to do is sort of tuck this in your brain. It turns out that there are, so in general, there are n minus 1 factorial ways to seat n people, or arrange n people at a round table. And factorials are just decreasing products, right? So for us, we had 4 people, right? So we could have said, oh, this is going to be 4 minus 1 factorial. That would just be 3 factorial. And that's just equal to 3 times 2 times 1, which is 6. And we got the answer of 6 down here. Pretty cool, huh? All right. Anyway, I hope you have a wonderful day, evening, morning, whatever time it is for you. And I'll be talking to you soon. Bye.